file for the effective removal of such pollutants. Various approaches have been examined to eliminate chromium hexavalent and methylene blue from wastewater, including membrane filtration, ion flotation, flocculation and coagulation, photocatalytic degradation, and electrochemical methods. However, these techniques require high energy consumption, significant investment, considerable maintenance, and operational costs. Particularly, absorption that is characterized by its lack of toxicity, high stability, and low cost is preferred over other techniques. Lamellar double hydroxides are the most promising materials using in adsorption. In this work, we focus on the comparative study of the absorption of chromium hexavalent and methylene blue using iron aluminium lamellar double hydroxides. To achieve this goal, the objective of this work is to evaluate the absorption performance of iron aluminium lamellar double hydroxides on the removal of heavy metals and organic dyes by optimizing different parameters and comparing their effects on adsorption efficiency. Before addressing the core of this study, it is important to briefly define adsorption, that it constitutes the central process investigated. Adsorption is a physical phenomenon in which molecules adhere to the surface of solid materials via physical forces or chemical bonds. There is a wide range of adsorbents such as alumina, zeolites, and silica gels, but lamellar double hydroxides are the most extensively used for the treatment of water contaminated by heavy metals and organic dyes due to their high adsorption efficiency, specific physicochemical properties, low cost, and easy of preparation. Chromium hexavalent and methylene blue adsorption tests were conducted in batch system under well-defined operating conditions. A solution at a known concentration of each pollutant is brought into contact with a fixed mass of iron aluminium lamellar double hydroxides. After adsorption, the filtrates were analyzed by UV visible spectrophotometer. Now, we proceeded to a comparative evaluation of chromium hexavalent on methylene blue, on the removal of methylene blue and chromium hexavalent using iron aluminium LDH. In this part, we investigated the influence of different K parameters in order to identify the most favorable conditions for each pollutant. The effect of contact time between the adsorbent and adsorbate, as well as the initial concentration of chromium blue and of chromium hexavalent, and methylene blue were investigated. The results shown in this figure reveal the same trend for the both systems. Adsorption kinetics are rapid in the early stage and gradually slow, where the equilibrium is approached around 30 minutes. We also observed that adsorption efficiency increases with the increasing of initial concentration, reflecting the stronger gradient of concentration between the solution and the adsorbent surface. sorry. We have also observed that. Sorry. We also observed that methylene blue is absorbed more efficiently than chromium hexavalent due to its cationic nature, which increases its affinity for the adsorbent surface compared to chromium hexavalent. We have also examined the effect of adsorbent dosage. The equilibrium adsorption as function as adsorbent dosage reveal that the amount of 2 grams per liter provides the optimal adsorbent dosage for the two systems studied. pH is an important factor in adsorption process as it influences the charge of the adsorbate molecules and adsorbent dosage and adsorbent surface. Regarding the adsorption of chromium hexavalent on iron aluminium LDH, the adsorption efficiencies decreases gradually with the increasing of pH. The results obtained reveal that 1.56 is the optimal pH for this system. This behavior is attributed by the fact that at pH 1.56, the chromium hexavalent species present in solution are anionic in nature. Given that the pH 0.0 charge, given that the pH 0.0 charge is determined to be 5.98, the adsorbent surface is positively charged under these acidic conditions. Moreover, the adsorption process observed in this study appears to be governed by attraction electrostatic. Regarding the absorption of methylene blue on iron aluminium LDH, we observed that the adsorption efficiency increases with increasing pH, reaching optimal efficiency with a pH of 7.22 under similar experimental conditions as for chromium 6 adsorption. In order to determine the optimal stirring speed on the adsorption efficiency of chromium hexavalent and methylene blue on iron aluminium LDH, the adsorption tests were conducted over a range of 0 to 600 RPM. The results shown in this figure reveal that 300 RPM is the optimal stirring speed for both systems. In conclusion, Iron aluminium lamellar double hydroxides showed excellent adsorption performance toward methylene blue and moderate efficiency toward hexavalent chromium. This difference highlights the strong electrostatic influence between the pollutant and the adsorbent surface. Iron aluminium LDH remains a promising, low-cost and stable material for the removal of various pollutants from water. And I thank you for your kind attention.
Any questions? Can you recycle your solvent?
Is a physical phenomenon in which molecules that are the adsorbate or the pollutant adhere to the surface of solid materials via physical forces or chemical bonds.
Can you recycle your absorbent?
I don't hear well.
Can you recycle the absorbent?
If I can, yeah, I can. The regeneration, you mean? 4 times, I think, because it's 4 times. For methylene blue, but for chromium 6, chromium hexavalent, the adsorption is not efficiently. So from chromium for methylene blue, because it is cationic, we can recycle many times the adsorption process. Yeah, because how you have seen, the optimal adsorption efficiency was achieved to 100%, 99%. So effectively, we can recycle the adsorbent.
Any more questions? Okay, thank you, Zuhra, for your presentation. Yeah.
Okay.
Finish. Good news for you. We have to break this session for coffee break. Meet you later.
Madame Kalaka, bonjour.
Bonjour. Ça va, madame?
Ça va, merci, et vous?
Ça va, c'est gentil, mais je n'ai pas compris pourquoi. Maintenant, c'est le pause café, si j'ai bien compris.
Effectivement, c'était pas. C'est vrai que sur le programme officiel, normalement, la pause café, c'est après toutes les présentations.
Eh ben oui,
Finalement, ils ont changé de programme.
d'accord. Maintenant, s'il vous plaît, maintenant, vous allez terminer à quelle heure, s'il vous plaît?
Pardon?
Vous allez terminer à quelle heure? Est-ce que je peux changer puisque j'ai un autre travail maintenant? Vraiment, j'ai beaucoup attendu depuis. En fait, ça.
Ne quittez pas, je vais voir avec la présidente, je vais vous répondre.
Ok, merci, c'est gentil.
Merci, je vous en prie.
Merci. Ok, à tout.
Good morning. Mrs. Chiara, are you here?
Hello, good morning.
Good morning. You can start your presentation.
Thank you very much. I will start it now. However, please help me through slides because I can't share my screen.
Okay.
Thank you.
No problem. Your presentation is here. I have it.
Okay.
So you can just 1 minute.
I will tell you, please, then you go through slides, please.
Something happened. You see the screen?
Yeah, I can see the screen, yeah.
I have your presentation here, but something happened. I don't know why, but I can't open the mode for presentation. Panorama mode. What happened?
Did you upload it or you can?
Yes.
I see that it's possible right now.
Now it's
great.
Okay, you can start.
Okay, thank you so much.
You're welcome.
So, hello everyone. Thank you for giving me the opportunity to participate today. First, allow me to introduce myself. I am Hammiche Dalila, teacher and researcher at the University of Hijaya and a member of the LMPA lab. Today, I present one of the studies conducted in our lab, which focuses on sustainable packaging. The title is Barrier Properties of PLA K2ZAN, FE mouth, clay nanocomposites for sustainable packaging applications. Before introducing our objective, please before introducing our objectives, let's take a few seconds to recall the problem. We are addressing the extensive use of petroleum used based in Algeria. So it is known that most packaging in Algeria is still made from the petroleum-based plastics, polyethylene, polypropylene, and polyethylene terephthalate for both water and so on. Also, Algeria imports about 1 million tons of plastic raw material each year, so we depend on these plastics. And the worst point is that about 500,000 tons each year are not collected or are mismanaged. So the objective of this study, my team and I dedicated to advancing sustainable packaging solutions. Currently, we are focused on developing PLA K2ZAN, iron mold, clay nanocomposites to enhance their barrier properties for food packaging applications. And the presented study today serves as preliminary investigation designed to explore the functionalities of these nanocomposites, specifically their structure and barrier properties. So let's go through the biodegradation. It is just a reminder. So this image illustrates, as is known, the difference between degradation and biodegradation. So it is known that degradation refers to physical or chemical breakdown of plastics into small fragments. So often, of course, due to sunlight, heat, and mechanical stress. The slide before, the biodegradation, please. before, yeah, this one. So I'm talking about the microplastics based fragments from the degradation. And it's now known for everyone that microplastics or nanoplastics are everywhere, even in our body, brain, and cells. So the biodegradation is our second, and I think the only option, because it is a biobiological process where microorganisms such as bacteria, of course, break down these fragments into natural substances. So in this study, you can go through the next slide, please. In this study, our matrix is the PLA, and the chitosan is used just as antimicrobial agent. Nanofillers used in this study are MOF-based iron BDC and clay P30B. And this diagram helps explain how the combination between these two fillers improves the barrier properties of the PLA chitosan matrix. Now, in the case of the MOF alone-only system, molecules can diffuse through the porous MOF particles. And if you take the clay as only system 2, diffusion is forced to go around the impermeable clay layers, increasing the path length slightly. But if you take the combination, both of them, both effects occur also. So diffusion must travel around the clay layers and interact with the mouth structure, creating tortuous and complex pathway that strongly reduce permeability and migration. This synergistic mechanism explains the enhanced barrier properties observed in our system, as we will see in our results. So let's explain the most barrier properties introduced in this study. So the first is permeability, absorption, migration, and sorption. Let's begin with the permeability, please. So our test performed using the CAP method according to ISO 7783 that measures mass change over time under controlled conditions like temperature and the humidity, and this test is known. The second one, absorption. The test followed STM D57098 to assess the water absorption of polymer samples, and this one also is very known. And the third one, migration. The tests followed EM 1186 total immersion method to evaluate the total substance migration from PLA, chitosan, and composite fields. Two food simultans were used. The first one is 50% ethanol, and the second one is 3% acid acetic. And the last one is sorption, where water vapor sorption was measured at 50% relative humidity and 23 degrees Celsius using climate chamber. The test is explained in this slide. Then let's go to see the experimental part of this study. The next slide, please. Great. So the next slide, please. So here we will talk about the synthesis of our MOF-based iron, BDC. Three main steps actually are followed. The first one, preparation of the first solution. So it is about dissolving terephthalic acid in the MF. The previous one, please. Yeah, I'm explaining the synthesis of FeBDC. So under stirring for 15 minutes. And the second solution, here our iron dissolved in water, then the cluster added were dissolved in distilled water and stirred for 15 minutes. The final mixture and recovery, the two solutions were combined and stirred overnight so after 24 hours, the resulting precipitate was filtered under vacuum, washed with DMF, and dried at 100 degrees Celsius overnight. The ground into the powder, the ground into fine powder. This is about the synthesis of MOF. Synthesis of the composites, MOF and clay. This protocol ensures good dispersion and possible physical-chemical interaction between the two fillers, even without coupling agents. So first, we disperse the clay in water and ethanol mixture, stirred and sonicated below 25 degrees Celsius. Also, the MOF dispersed similarly and the same temperature and same conditions. Then the both solutions were added to each other, and the mixture was centrifugated to remove solvents, then dried it at 50 degrees Celsius for 12 hours and obtain our composites powder. Next, please. So here the formulations were prepared using twin screw micro extruder designed for small scale melt processing. And for all materials used here, PLA as matrix and ketosane as agents of as antimicrobial agents were dried at 60 degrees Celsius for 24 hours before processing. And for each formulation, about 12 grams of PLA, pure or blended with fillers, were loaded into the preheated chamber at 180 degrees Celsius. Two series of experiments were performed. The first one, PLA, 2% ketosane with a MOF only in different loading, 0.5, 1, and 1.5. And the second series were PLA, 2% ketosane 2, and in this time with different contents of our composites, 1, 2, and 3% with 1:1 ratio. It's worth noting that the ketosane used in this study, prior to use it, it was washed with distilled water, dried at 55 degrees Celsius for 24 hours, and subsequently ground and sieved through 200 micrometer mesh to obtain uniform particle size suitable for composite preparation. Next, please. Then the extruded materials, PLA and all nanocomposites, were cut into uniform granules and dried to remove residual moisture. These granules were then placed to Teflon-lined molds between metal plates and pressed using hydraulic press at 180 degrees Celsius. Let's now move to results and discussions. So here we have the FE-MOF stir spectrum to see if our synthesis was successful or not. So here we can see some important bonds. The first one at mil 564 corresponds to the asymmetric searching vibration of carboxylase group. in the ligand, and its shifts upon middle coordinations indicates interaction with the middle center. The second one, at 1383 band, typical for carboxylase in coordination complex, further confirms the coordination of iron with the ligand. And one another band is very important at 748, likely related to aromatic deformation or FeO bending modes in a MOF structure. So based on these results, we can say that the synthesis of our MOF was successful. Let's continue with the infrared of our composites, MOF and clay. As you can see here, a broad band around 1600 in the clay indicates hydroxyl groups of clay, which shifts in the composites, suggesting interaction between the clay and the MOF via hydrogen bonding or coordination. And bands at 1389 and 1017 confirm the preservation of carboxylase groups in the composites via exchanges in intensity showing interaction with the clay. These results confirm the successful synthesis of our composites because both clay and the MOF preserve their structure. X-ray diffraction pattern of the composite, as can be shown in this figure, the MOF exhibits distinct peaks, confirming its crystalline structure. And in the composite, the pattern shows that the characteristic peaks of MOF and broad peak from clay, indicating successful incorporation of the clay in our MOFs. So we can say that this indicates in successful incorporation of clay on our MOF. Now let's see infrared analysis of our nanocomposites. Just slight shifts of the carbonyl stretching band from 1744 or 47 to 1741 was observed in the 2 and 3% composite formulations, and this shift suggests weak interactions between the PLA matrix and pillars, likely through hydrogen bondings or similar interactions, like van der Waals interactions. TGA analysis. Here, as we can see here, in the DTG curves, we can see that these curves show wider degradation peaks, suggesting ultra degradation behavior. And after the incorporation of the MOF into the PLA, the degradation accelerates. We can say that this incorporation accelerates the depolymerization of PLA, but still no significant structural impacts, making the composite suitable for food packaging. Microhardness tests, as this figure shown, the microhardness of PLA-based nanocomposites improves with the iron MOF and iron MOF clay contents. The addition of these fillers enhance rigidity and overall mechanical strength of PLA. The improvement is supported by FTIR analysis showing hydrogen bonding between the matrix and fillers, which enhances maybe polymer network cohesion and mechanical properties. Contact angle measurements. The change in contact angle of the films at 10 seconds and 30 seconds. And the results for PLA composites modified with 2% chitosan and incorporated fillers too show significant change in surface wettability. The addition of chitosan reduced the contact angle, increasing hydrophilicity, and adding both fillers or the composites further reduces the contact angle, making the surface more hydrophilic. The migration test, as we can see in this table, all films show migration values below 10, missing the EU regulation, and adding 2% chitosan increases the migration due to the hydrophilic nature and OH and NH2 groups, which favor diffusion. And the addition of clay and the MOF reduces migrations thanks to their barrier effects, creating tortuous diffusion paths that slow molecule passage. These composites balance biodegradability and barrier safety, making them suitable for food packaging application. Water vapor permeability test, as you can see in this table too, while chitosan increases hydrophilicity, MOF and the composite MOF clay improve the barrier properties of the composites by reducing water vapor permeability. So fillers enhance the overall structural integrity of the composite, creating stronger and more denser barrier against water vapor. Water absorption test. This figure presents the 7-day water absorption results of PLA chitosan, and their nanocomposites. PLA 2% chitosan show the highest absorption, reaching about 1% or almost 1 by the second day due to the hydrophilic nature or groups of chitosan. Pure PLA reached an intermediate level of 0.7, incorporating MOF and composites progressively reduced absorption to as low as 0.30% after 7 days. This reduction is attributed to the tortuous path formed by the nanoporous fillers, which hinder water diffusion through the polymer matrix. Overall, the results indicate enhanced barrier effects and stable structure over time, confirming the good compatibility and interaction between the polymer and fillers. As conclusion, we can see that this sample study developed PLA-based packaging films reinforced with both MOF and MOF clay composites combined with chitosan can enhance barrier properties, mechanical and antimicrobial properties. We didn't put results here, but it really enhances even antimicrobial properties. While maintaining biodegradability, we are right now doing or carrying out some biodegradable testing. Key findings of this study: the composite clay MOF was successfully synthesized and integrated into PLA chitosan films. Microhardness improved while minor thermal variation was shown. Also, the composites reduced water vapor permeability and improved hydrophilicity, with tortuous diffusion path which limits the water absorption and migration, and ensuring food safety. We can say that this PLA, K2 composites Fe, MOF, and clay films show promise as eco-friendly packaging materials, combining durability, moisture control, and biodegradability. And future work, or our work right now, is to confirm actually the antimicrobial activity and toxicity for food safety, and optimizing the MOF and the clay loading. Also, do some testing about real condition, biodegradability, and environmental impact. And thank you so much for your attention.
Thank you, Samia, for this presentation. Any questions? Do you hear us? Samia?
Yeah, I can hear you, of course, yeah. Sorry, right now I can't hear.
The question is regarding the use of iron moss. Okay?
Yeah.
So
Okay.
iron moss is known, but did you check whether there are studies about the antibacterial activity or not of this moss?
Yeah, actually, I have said in my presentation that we have carried out many antibacterial studies, but I didn't put them here. And actually, the results are successful and encouraging in the area of antimicrobial activity.
Okay, Samia. One more question.
Thank you, Samia, for your presentation. Can I ask you, I just have some curiosity, if you can change ketosane with ketene or not?
The ketosane, is it with ketene or not? Actually, I take it directly without any chemical treatments. Dust was washed with distilled water and dried, of course, ground and sieved through 200 micrometer mesh. It is as a raw ketosane.
The blend PLA with the ketosane is in distilled water also?
The blend? You're talking about the blend.
Yeah.
The blend, yeah.
For example, if you change the solvent.
Yeah.
We can start with ketene, in the end you have ketosane with PLA.
Actually, I'm working on finding something green, you know. So using solvents a lot, it is not good for our studies to do something sustainable and green packaging, you know. So you didn't do any treatments, any chemical treatments, and the formulation were prepared by melt mixing. So no need to do some solvents or.
Okay, thank you very much.
Thank you.
How did you prepare the iron moss?
Yeah.
Did you use solvents or not?
Yes, of course. But
of course,
actually,
then.
the percentage is very small, you know.
Yeah,
This is the first thing. Yeah, I agree with you actually.
Yeah.
And we are going to synthesize some biomorphs. Yeah, in the near future. I totally agree with you. Thank you for this observation.
Okay, Samia, thank you very much for your
Thank you, sir.
presentation. Have another clamp for Samia.
Thank you so much.
And now we move to Ganesh.
Yes, sir.
You hear me?
Yes. Can you hear me?
Yes. Very good.
Can I share my screen?
Yes. Just make your presentation. Scene and start.
Now screen is visible?
Yeah, it is seen. You can start.
Okay. First of all, I want to thank my guide, Dr. Vikram Pandit and Professor Dalila for giving me this wonderful opportunity to present my presentation in international conference. Myself, Ganesh Parshuram Jadhav, here to present synthesis and characterization of PR hydroxide and their photocatalytic applications under the guidance of Dr. Vikram Pandit, and my research center is Haribhai V. Desai College, Pune, India. Here is the outline of my presentation. In upcoming slides, we are going to see designing of my research problem, literature survey, aim and objectives, and many more such things. First of all, where I can tackle or come my mind this kind of problem in Pune, according to this 15 January, one woman from dies due to GBS syndrome, and which is circulate from polluted water. And when I start literature about pollution and reasons of water pollution, then I come to know that as a population grows, globalization and industrialization also increases, and that leads to pollution. More than 50 kind of diseases are caused by poor quality of water, and many human activities leads to water pollution. So here are the some major causes of water pollution: agriculture runoff, oil spills, radioactive wastes, industrial waste, and heavy metals, pharmaceuticals. Among all of these causes, we are focusing on synthetic dyes. So dyes are used for coloring our clothes and many more applications, but they have some disadvantages also. A major disadvantage of dye: they are stable at a very long period of time, and due to that stability, they have very adverse effect on human beings, aquatic animals, plants, and environment also. So need of degradation of that dyes. So there are various methods to degrade these dyes: chemical, physical, biological. Among this, in this presentation, we are going to focus on photocatalysis. In photocatalysis, when sunlight is fall on valence band, electron moves to the conduction band, and oxidation and reduction takes place. Here in this image I shown a principle of photocatalysis. uh, the photocatalysis have wide range of applications. Among these, water purification, air purification, CO2 reduction, and hydrogen production. So for this photocatalysis, we require one photocatalyst, and for this purpose I choose praseodymium, because he had a wide range of applications such as oxygen storage, catalytic oxidation, electrochemistry, and photocatalysis, and he has a band gap between 1.7 electron volt to 2.7 electron volt. This made it a highly effective photocatalyst. Before I start synthesis of that PR, I do some literature survey. In this literature survey, I come to know that these are the series of synthesis and degradation study. More few results I mention of hydroxide and oxide. uh, Aim and objective of my work is to preparation of inorganic semiconductor nanocomposite by in situ and ex situ method to make visible light active semiconductor system having higher photocatalytic activity, characterize and photocatalytic activity for prepare nanocomposite systems. For preparation of PR hydroxide, various method can be used such as sol gel method, hydrothermal method, molten salt method, and precipitation method. For synthesis of hydroxide, I have chosen hydrothermal method because of this method is very simple to perform, and we get a nice morphology in it. So after synthesis, we have to characterize our catalyst. For characterization, different characterization techniques has been used. Among these, XRD, TGA for thermal analysis, same for scanning electron microscopy for morphological study, FTIR for functional group detection, and UV for dye degradation study. This is a typical method that I have used for synthesis, in which I took PR nitrate as a precursor and drop wise addition of NaOH. Then we got precipitate, and this that precipitate transfer into hydrothermal reactor, and that autoclave is tightly closed, and then that hydrothermal reactor is put into a oven at 180 degrees Celsius for 12 hours, and after that reaction happen, then we get this greenish yellow color powder, and that powder we dried at 80 degrees Celsius for 8 hours, and this is the same morphology of my catalyst. We can clearly see that there are rod-like structures. So after complete synthesis, we move forward to characterization. In characterization, we did its FTIR analysis, and prominent peak at 550 shows the confirmation of uh, PROH compound, and in XRD we match this XRD with GCPDS, and we come to know that it is PR hydroxide. Then we go towards the UVDRS analysis, and also we did its same analysis. In same analysis, we can clearly see that uh, nanorod like structure. After successful synthesis, we do its photocatalytic application. In photocatalytic application, we tested our photocatalyst in for two dyes. One is the rhodamine 6G dye, and another one is a crystal violet dye. And in both studies, rhodamine 6G dye degraded up to 10%, and crystal violet dye is degraded up to 30%. And here are the some graphs showing LN. I conclude my presentation in I have successful synthesized hydrothermal PR hydroxide by using hydrothermal method, and successful characterization by using XRD, FTIR, and DRS. And after photocatalysis, I come to know that rhodamine dye is degraded up to 10%, and crystal violet dye is degraded 50%. Expected outcome from research work. Now, its rate of degradation and percentage is very low. So, in upcoming days, I will try to make composite system, and try to enhance rate of degradation and reduce time. Uh, for a photocatalytic activity, and also I try to make PR oxides and hydroxides with many more composites, and writing a research paper also my outcome. Here are some references that I have used in my research, and I want to thank our college, Pune Gujarati Kerwani Mandal, to providing me lab facility, our principal, Dr. Rajendra Gurau, to constant support, and my guide, Dr. Vikram Pandit, to guiding us. Thank you.
Thank you, Ganesh, for the good presentation. Any questions?
Hello. Am I audible?
Yes, sir.
You have done the time of the nanoparticles, PROH thrice.
No, sir. Just same.
Okay, as I have seen. How do you get to know about the size of the nanoparticles?
On same images, we have a small scale. According to that scale, I measure
That's approx, I
size.
think. That's approx. Is it? That's not exact.
I am
You
still working
don't know
on it.
whether it's within the nano range or not.
No, no. Right now, I am working on it, and this is my initial stage of work. I have sent a sample to for TEM, and results are waiting right now.
Okay. Yeah. Because that's very important. Otherwise, we don't know whether it's within the nano range or not.
Yes, sir.
Yeah, that's very important. No? Anyhow, you can calculate from the XRD also. XRD pattern, you can approximately, approx particle size you can calculate.
Yeah, from equation
Yeah,
FWH.
that you can use and you can calculate. But that's not exact. Okay, thank you. All the best. Best of luck.
Thank you, sir.
Thank you. One more question.
Are you sure you have photodegradation? It's just not an absorption process? You know, because it doesn't make any sense just you stop at already 20 or 30%, you know. It's probably just have absorption either of the initial dye or pollutant on the surface, or the intermediates if there's any potential degradation that absorbs on the surface of your catalyst, actually, for photocatalyst. I really doubt that you have photodegradation. For me, it's mostly an absorption process.
I did its recycle study, and for 3 to 2 times, and after that I took its FTIR, and it is same. So I think there is a no absorption.
No, you cannot detect with FTIR if it's a very small amount. It's a monolayer. You cannot detect it with FTIR if it's just a monolayer. It will be very difficult unless you work on the reflection mode, in the total reflection mode. Otherwise, it will be difficult. So what you can do is just, you know, how do you know it's really? Did you use UV vis, or which technique did you use to quantify?
Yes, I use invisible spectroscopy.
Okay. Yeah, it's really, I don't know. But did you make an absorption, desorption, or just an absorption process? You leave, you know, when you mix your dye with your particles, you leave them for a certain time until you reach the equilibrium, and you check whether indeed there's a decrease in the intensity or not. When you mix
Yes,
your...
sir. I did this experiment. I after adding photocatalyst, I wait for 30 minutes, and after that, I taking those readings.
1 hour. Yeah, it's okay. Okay.
You wanna comment? Okay. Okay, thank you for your time and your good presentation. And goodbye. Our second next presentation is, I will check, is they online? Is not here. Maybe we can move to Ankit. So we will hear Ankit about chitosan-based encapsulation sterilization in sustainable agriculture. Ankit, do you hear me?
Am I audible, sir? Hello.
Hello, yeah. Ankit.
Yes, sir. Am I audible?
Yeah, good evening.
Yes, sir. Good evening, sir. How are you, sir?
I'm fine.
But sir, one problem is that my title is not that. I have also made the committee that my title is hydrogel-based adsorbent for removal of emerging pollutants from aqueous media. Yes, sir. You can check on the Word file. I think they have sent me on the other day.
Can you show the presentation?
Yes. Is the screen visible, sir?
It's okay.
Yes, sir. Is the screen visible?
Yeah. Good. You can start.
Yeah.
Please.
Yes. First of all, I thank you, the committee members, for giving me this opportunity for to represent my review paper, that is hydrogel-based adsorbent for the removal of emerging pollutants from aqueous media. And I thank my guide professor HAG, Dr. Balbir Singh Kaid, for giving me this opportunity. And in this context, we will look about the introduction of what is the water pollution exactly, and what we are going to remove from it. And again, then it is hydrogel and the classification of. Then we move towards the classification of hydrogel and characterization and process governing adsorption, uh, kinetics adsorption model and thermodynamic studies, and conclusion, and what are the future perspective about that. And this review paper is based on the what recent advances have done in the previous in between 2015 and 2025 research paper, that how hydrogel has manipulated using nanoparticles or some other materials. So first of all, that introduction, that uh, what is water pollution exactly that we are looking for. Like it is a major environmental problem, that in which there are many uncontrolled release of pharmaceuticals, dyes, pesticides, and personal care products, and they are carcinogenic, which is can be dangerous to our health. And these all groups are as emerging pollutants, and they affect our health. And for that, the basic part of that is our body is 80% water, and it affects our human health. And that impact of poor drinking quality can result into waterborne disease. And what WHO said this about that, that 80% of world's diseases are linked to poor drinking water quality, and 50% of child deaths globally are due to unsafe drinking water. So over 50 diseases are caused by poor drinking water quality. So situation in developing countries are like that. The quantity of water drinking in developing countries is a major concern. which leading the mortality and morbidity in these region. And these are specific causes that can be caused from the pollutants, which are dyes and different pharmaceutical products, heavy metal ions, which are carcinogenic, that help affect our health, that is cholera, diarrhea, skin disease, cancer, and child health issues. And so what we are looking for to counter that, so we can't, so in this review we are not talking about the microbes and the viruses, mostly that the pollutants, dyes and all. So first of all is the sustainability and green approaches and the cost effective and biodegradable. What we are, whatever we are synthesizing, it should be biodegradable and do not harm any do not harm the environment after degradation, and it should be cost effective if we are commercializing it. And the process of synthesis should be green, to like to maintain the green chemistry and the sustainability, that whatever we are synthesizing, it should it should be used up to 10 to 15 cycle times, and more than that. So conventional methods often are like ineffective eliminating these contaminants from water resources. So what we are looking for is the hydrogel, that what are the hydrogels, and this has a high affinity to absorb the water more than its capacity, and it has emerged as a good absorption material over the past few decades. So in the next slide I'll talk about the what is hydrogel. And the hydrogel are the 3D dimensional network of hydrophilic polymers that can swell in water, and it swells due to various hydrophilic groups, that is OH, CONH or CONH2, and further there are many groups that can participate in making it hydrophilic, and it absorbs mostly 80-90% of its capacity. And the main important thing is that they do not dissolve in water due to its cross-link structure, which is mainly come from the cross-linking, by cross-linking it or polymerizing it. So again, next is the classification of hydrogel, that based on their biodegradability, source, charges, and types of cross-linking. So there are 4, but there are many, but like I'm representing only 4 here. First of all, that is source, based on natural and synthetic, in which natural based are which are extracted from animal and plant extract, in the chitosan, sodium alginate, cellulose, and hyaluronic acid. Most of the presentation is based on chitosan in the conference. These application can be wound healing, in the tissue engineering and the drug delivery, and these are biocompatible and biodegradable materials. And the second one is synthetic, which are lab materials synthesized like PEG, PVA, PEA, which can be used as the super absorbent polymer, contact lenses, and biosensors. Now the second one is type of based on the type of cross-linking, mainly of the two, chemical cross-link and physical cross-link, in which chemical there is an interaction which are irreversible in nature, and they are stronger, they have stronger interaction than the physical, like chemical bond, bypass stacking, and all. Examples are cellulose, glutaraldehyde, and formaldehyde, and etc. These applications are biomedical scaffold in the treatment of osteosarcoma, mostly the bone cancer. We are now making a scaffold from the polymer, and if it's used as a scaffold in the cancer treatment, why not? It is in the drug delivery system. So again, another is physical crossing. Mainly it is irreversible nature, irreversible in nature, and the type of interaction is mainly H bonding and weak van der Waals forces, and these are some example: PLA, PBA, and HA. and the applications are injectable hydrogel, pH or temperature sensitive systems. Now, based on the electric charge, ionic, non-ionic, and ampholytic. In ionic, there are two categories: cationic and anionic. Cationic, which carries the positive charge, and anionic, which the with the hydrogel which carries negative charge. And these are the examples in which these due to this conjugation they act as a negative charge. And the application, the dye absorption, gene delivery, and absorption of anionic and ionic contaminants from the wastewater purification, because of dyes and heavy metal signs are the positive and negative charge, and according to that we can take our paste hydrogel, whether it is cationic or anionic or a non-ionic, which do not carry any charge, like PPA, PEG, PA, and PHEMA. So, sorry. And the application must here in the drug delivery, where charge interface must be avoided. And the ampholytics, which contain both positive and negative charges, like polybutanes, lecithin, and the application are in the antifouling coatings and the blood contacting devices. Now the last one is based on biodegradability. First one is biodegradable and non-biodegradable. First, the biodegradable is like which can be consumed through microorganism, and through which do not result any harm to the environment. For instance, PCl and polybutamino ester, PHBV, and mostly if they are biodegradable, they use in the drug delivery and environment friendly materials and temporary implants, that because of biodegradability. And second one is non-biodegradable, which do not consumed with the time from environment itself, that is PBA, PA, and mostly non-biodegradables are also the synthetic one. And application are long-term biomedical devices, contact lens, and synthetic gel. Both synthetic and non-biodegradable are similar to their properties. And now the properties of hydrogel, that these are biocompatible. Biocompatible means it do not react with our blood and mechanical properties, which can be enhanced by several cross-linking and polymerization, and we can use it as a scaffold, which enhances mechanical property. And the swelling property, as I said earlier, that it holds more than its capacity, over 80 to 90%, and stimuli responsive properties, that according to pH, temperature, and other means, they are responsive to that property. And application are in various field: agriculture, biomedical, cosmetics, environmental application, where our focus is, and food industry, and the soft robotics. In the agriculture, mostly that control release drug, that first they absorb fertilizer and they release controlled. And in the biomedical application and all other applications are as follows, that I also include in the types of hydrogel. And now the characterization of hydrogel involves FTIR, DLS, TAM, TJ, DSC, and XRD, and the SAM, TAM are quite similar, that it explain the morphology, topology of the system, but SAM provides the 2D image of the system, of the material. 3D material of the 3D image of the system, and TAM provides the 2D image of the system. But in the TAM, that material is encapsulated with the nano materials. TAM resolution quality is higher than SAM. The next one is FTIR, like whatever we are fabricating from cross-linker monomer, then it provides the functional group of the material. And the DLS is it is related to nanopolymer. The range of it describes the range of nanopolymer, that it is ideal or not. Mainly the ideal nano size range is less than 100 nanometer. and the PXRD about the crystallinity and whether it is amorphous or whether it is crystalline. That most of our polymer are crystalline, and it can show the peak like this. But if it is graphene oxide nanomaterial, it shows some peak like that. That's the reference. And the TJ and DSA analysis mainly focus on the thermal stability by comparing it with the percentage decrease in weight with respect to temperature, or the heat with respect to temperature. And these are the characterization which involve the hydrogel, but there are some other characterization that involves that NMR and all other things. If we are synthesizing the monomer from organic synthesis, we can use that in the process. Now the process governing adsorption in hydrogel systems, that within that mostly there are three types of adsorption: physical, chemical, and diffusion mechanism. Like physical, in which there is a less weak bond like H bonding and water interaction, and the chemical adsorption involves chelation, ion exchange, and there some kind of electrostatic interaction and pi stacking. Pi stacking mostly involves the aromatic rings, and these hydrogel and their renewable structure functional group enable selective adsorption through ion exchange, hydrogel bonding, and pi interaction. Additionally, their biocompatibility and reusability make them ideal for sustainable purification. And here is the kind of a reference from a paper that is from the Kiwang, that is removal of anionic dye from aqueous media by using a novel high charge, positively charged hydrogel with capacity. That it has also shown the beautiful adsorption mechanism, that this dye is showing the different interaction, that by stacking and H bonding and kind of wonderful interaction also. Now the as the adsorption mechanism is done, we will move how they we have to confirm that that this dye is actually absorbing something, but it is physical, but we need to make it happen through calculation, and then these models comes, kinetic and isotherm model. We will particularly focus on the pseudo first order, second order, and intraparticle diffusion. And second one is isotherm model, which is Langmuir, Freundlich, Tamkin, and Evolich model, which help evaluate surface heterogeneity and adsorption capacity. First one is pseudo first order model, which gives the rate of occupation of adsorption site, which is proportional to number of unoccupied sites, often indicating the specific chemical reaction. And this is the chemical equation, that is log QE minus Q2 is equal to log QE minus K1.2.303 T, in which Q is adsorbate, Q is equilibrium adsorption capacity, and Q2 is adsorption capacity at particular time, whether we are in the series of time, like 10, 20, 30, 50, whatever the minutes in which you are dye or heavy metal ions is adsorbing. And the K1 is rate constant for pseudo first order model. And the second order model, it suggests that whether our adsorption is chemical or not, involving valence force through sharing or exchange of electron. And these are this is the chemical equation: T by Q2 is equal to 1 upon K2 QE square plus T by QE, where K2 is the rate adsorption constant for pseudo second order model. And third one is intraparticular diffusion model. That is account for diffusion of adsorbate within the pores of hydrogel, which can be controlled step in adsorption process. And this is the equation, and these are the graph that is taken from the paper. That first one is for the pseudo first order model, and second one is second order, and third one is the intraparticle diffusion model plot. And the second model is the isotherm model, which explain us the adsorbate and adsorbent interaction at constant temperature. That first one is Langmuir isotherm, which mainly suggests that it is a monolayer adsorption, that adsorbent has finitely adsorbing the adsorbate, that is which is here is the common chemical equation for the Langmuir isotherm, in which Q is the adsorption capacity, Qm is the maximum adsorption capacity, where Q is for the equilibrium, and C is the equilibrium concentration, and B is the Langmuir constant. And we also look for the RL after calculating these stuff, that these values should lie in between 0 to 1, which shows the favorability of this isotherm. And this is the chemical equation for that. RL is equal to 1 upon B plus 1 plus B C naught. And a fluid isotherm, which focuses on the heterogeneous space and multilayer adsorption, that is can be also called as the physics option, that is also multi-layer adsorption. But in the Langmuir, it is a monolayer, and we can call it as also call it as Campbell option. And the Temkin model, which it it just suggests the adsorbate and adsorbent interaction, that it is proper or not. And this is the chemical equation, and the Evolich isotherm, that is useful for that, where adsorption site increase exponential with adsorption. And here is the chemical reaction in which suggests that Evolich isotherm. And these are this is the how we can interpret the data for Temkin and Evolich isotherm. And another one is thermodynamic studies, in which we find the parameters such as delta G, that is Gibbs free energy, and delta H, molar enthalpy, and delta S, which is entropy, in which delta G is should be negative for the spontaneous adsorption, and delta H can be positive or negative, whether it is exothermic or endothermic reaction, based on the interaction between them. And delta S reflects the randomness of randomness between the solid liquid surface. And this is the equation for that, that is ln case is equal to S upon R minus H naught upon RT, which is in which Kc is adsorption constant and R is universal gas constant, in which and these are the free energy. And this is the Van 't Hoff equation, in which we interpret the data for that. And for the conclusion and the future work, prioritize that hydrogel-based adsorbent are increasingly recognized as sustainable and versatile material for addressing emerging water pollutants. And the development of multifunctional hydrogel is directed toward tackling multiple pollutants simultaneously, making them highly adaptable for diverse water contamination scenario. Means key features are that whatever we are synthesizing, it should have high absorption capacity, and it should be selective toward whatever we are going to target. These two are same, and this is a recyclable material, and whatever we are synthesizing, it should have some reusability up to 5, 10 or 15 times. Then it is ideal material for to tackle water pollution, mainly the contaminants from it. And the future application can be the advanced wastewater treatment, heavy metal ion removal, and that and also the emerging contaminants mitigation. And these are the conclusion and the future perspective of these presentation. And thank you. I also I'm thankful to the committee members and also my supervisor, Dr. Professor B.S. Kayat, for giving me this stage for presenting something in this conference. And I'm grateful for the opportunities. If it's whether my college, that is an IT Jalandhar, and whether my professor, and also the conference committee members.
Thank you. Thank you, Ankit, for your presentation. Let's see if there is any questions. Yes.
Hello. Am I audible?
Yes, yes.
Yeah. हाँ रुड वाले क्या हाल है?
सही हूँ सर, आप कैसे हो?
Fine. Nice to see you on the screen.
आपको भी सर, nice to see you sir. Like yeah, namaste sir.
Namaste. Okay. What do you say about the structural integrity of the hydrogels? Structural integrity. Because they behave
Sir,
like human tissues, animal tissues. Yeah.
Like it is, sir, the integrity of structure is like due to the cross-linked functional group, which provide its porous structure and 3D shape, which can absorb more than its capacity. That's why it is the best absorbent material. Yes,
that can be used in biomedicals, and they don't
Yes, sir.
lose their structural integrity, and they may swell 1,000 times, but structural integrity is maintained. Like human tissue,
Yes,
that's why
sir.
they are used in biomedicals with
Yes,
less
sir.
toxicity.
Yes, sir. Yes, sir. In the as a scaffold, also we can use it in the bone cancer.
Yes, road wallow, keep it up, Shabash. Excellent.
Thank you, sir. Thank you for giving me this stage, and I also thankful my supervisor for that.
Any more questions, comments? Okay. Thank you, Ankit, for your presentation and for your explanation for the question.
Thank you, sir.
And
Thank you, sir.
have a nice day. One more clap for Ankit.
Thank you. Okay, sir. Okay, sir. Okay. Thank you.
We'll check the. So we are finished now with the presentations. There are the last one is missing, so we will go to the booster session. Okay. See you outside in the booster session. Now? Yeah. So where's Dalila? Okay. Please. Dalila is coming. There is only such.
Cilia, s'il te plaît. So, dear all, as we conclude Polymer Mediterranean Fiber International Conference 2025, it is with immense gratitude and pride that I stand before you to reflect on the achievement of the past 2 days. This conference has been an incredible journey of learning, collaboration, and inspiration. Therefore, the work show is here has reaffirmed the vital role polymers play in shaping a better future for humanity. I would like to extend my heartfelt thanks to our esteemed speakers and participants for sharing their expertise, passion, and vision. Your contributions have enriched this conference and sparked ideas that will resonate for beyond these sessions. To the organizing committee and sponsors, your hard work, dedication, and meticulous planning have been beacon of this event's success. On behalf of the laboratoire des matériaux polymères avancés et la faculté de Technologie à l'université de Béjaïa, and also the organizing committee, I would like to thank you all for your participation. I wish you safe travels and the hope that we will meet again a future gathering. Before closing this event, I would like to give the floor to the head of our laboratory and the dean of faculty, followed by the award speakers and the best oral and poster presentation. Professor Kassi, maybe you would like to give some words?
Thank you, Dalila. I will be very short. Yes, we come at the end of the conference, and I would like to thank all of you for attending this conference. And I'm very confident that this conference was very fruitful and productive for you. And I hope really to see you maybe in the near future and to debate about this problematic of plastics materials, natural fibers, biocomposites, and all these issues aiming at contributing to solve some problems in relation to the management of these materials. So once again, thank you very much for attending, and I wish you a return home very well, very nice, and thank you.
So the dean of faculty, I don't know if we have to announce the closing or to give the trophy to the participants, the best oral and poster presentation.
Donc, merci Madame Hammiche. Bonjour tout le monde. Donc, au terme de cette conférence internationale, je tiens à exprimer au nom de la faculté de technologie toute ma satisfaction et ma profonde reconnaissance pour le succès de cette belle rencontre scientifique. Ces 2 journées ont été marquées par la richesse des échanges, la qualité des communications qui témoignent donc du haut niveau scientifique de cette importante rencontre. Je voudrais adresser mes félicitations les plus sincères donc au comité d'organisation et au comité scientifique pour le travail accompli. À leur tête, professeur Hammiche Dalila et professeur Kassi Mustafa. Je voudrais également remercier tous les participants, les intervenants et les conférenciers qui ont contribué donc à la réussite de cette manifestation. Donc au nom du recteur de l'université de Béjaïa, professeur Benaïch Abdelkarim, je déclare la clôture. Je déclare la clôture officielle de ces travaux de cette conférence. Je vous souhaite à toutes et à tous un bon retour dans vos pays respectifs et les quatre coins d'Algérie. Je vous souhaite également de nouveaux projets à l'avenir. Donc, avant de clôturer, j'ai clôturé, donc il y a un trophée qu'on va remettre.
Thank you for Dean of Faculty, Professor Bradey. Professor, it's okay. It's okay.
Donc, il y a deux trophées. Hein?
Thank you. So I would like right now to announce the best oral presentation according to the scientific committee. I invite Dr. Kumar to join us.
Ouais.
Yeah, in the middle, yes. So, for the best poster presentation, I invite Ketia Louis. Ketia Louis.
Donc, je me fais le plaisir et l'honneur de te remercier. Le trophée, je paye le poster. Toutes mes félicitations. All my congratulations. Thank you so much for your Let's take souvenir. Mettre au milieu.
I would like to thank all keywords, so I invite you to join us, Professor Kate, Professor Bukharoub, Professor Frederick, and Professor and Dr. Mustafa, and also Professor Mustafa from Oran. Please join us. Professor Kate, Professor Bukharoub, Professor Frederick, Professor Mustafa Belhaliba, and Dr. Please come on. Join us, please. Professor Bukharou. Professor Keith. Professor Lebon Frédéric. Professor Ben Haliba. So Professor Francisco is absent, and so he will be presented by Professor Frédéric. For Francis. Please, before going to the lunch, I invite you to take a photo of the group outside. avant d'aller au déjeuner, je vous invite à prendre une photo de tout le groupe juste à l'entrée de l'auditorium. I would like to say something that thank you so much for your coming. Thank you so much for your help. I will talk about the organizing committee, of course, and I hope that we will meet again, maybe after 2 years, but I don't know, but I hope so. Thank you so much.